in complex oxides, actually, I was more ambitious in my abstract. Actually, I will focus pretty much in strontium titanate and just giving some perspective on what we are currently working on. Okay, here I want to thank the collaborator that took part in results that are shown and that are already published. So, and also I want to take the opportunity to advertise our recently founded lab in the Institute of Physics of the University of São Paulo. That is the Laboratory for Quantum Matter Under Extreme Conditions, founded by myself and Professor Julio Larrea. So currently we have 2 groups that are working in the lab. So, and just to introduce our new laboratory to the community, Brazilian and also the international that is here present. Our aim is to have, from a point of view of the infrastructure, to have an infrastructure that can offer the possibility to perform experiments that are not commercial, and then that goes in towards the development of homemade setup that allow to investigate thermoelectric properties and AC specific heat under pressure, and one of the joint effort that is going on, it's about thermal transport in systems that are towards bidimensionality. So in terms of a project, we have several interests of investigation, several sub-projects. So that goes from correlated materials, topological insulator and semi-metal, thermoelectric materials, and complex oxides. So clearly these areas overlap each other. So this is a very general view. Okay, so first of all, let's give a very general definition. Probably you are all familiar with that, but it's good to remind that complex oxide in a very general way is a material that has an oxygen, at least 2 other different elements, or oxygen and 1 element into states of oxidation. And perovskite is a structure that also, I guess, you are familiar with that in the typical form of AB or oxygen 3. And actually, we have to say that the name is came after the calcium titanate, that it was the perovskite initially, and after the name is used for the whole category. So this is not used as an emblematic perovskite today because it's not in the ideal structure. Perovskite has the characteristic to show many structural phase transition, and therefore why we say that it's not the ideal, because the ideal for us is the cubic. So which material I can remove the mask, right? Yes. Okay. Thank you. So strontium titanium is a perovskite that maintains the cubic structure at room temperature. For this reason, also is widely used as substrate for thin film growth. And even though, okay, here there is a presentation of the structure, even though we have to say that also undergoes some structural phase transition that are known since a long time, and one of the most famous is the tetragonal transition that I will show in a minute. I will represent in the next slide. So this material is known since a long time. You can see that here is from the 60s. So why actually it turned out to be interesting again in this in its bulk form. Okay, so here is the representation. We can see that there are other, like prominent representative of this category of perovskite, calcium titanite and barium titanite, that actually the perovskites are quite famous to be really a fertile playground, because with little modification of the electronic structure or dimensionality and also heterostructure, that is a more new area of investigation, we can really induce several emerging quantum states. So in terms of the structural phase transition, so we have around 105 Kelvin, the rotation of the octahedra. So this is what we call the antiferro-distortive transition that lowers the symmetry of STO. So one of the characteristics for which was known since long time that is quite remarkable is the very high dielectric constant. So this is a material that is defined as quantum paraelectric. It wants to be ferroelectric, but then it saturates the epsilon, never reaching the ferroelectric state. So this can be shown that the ferroelectric state can be induced through calcium substitution or even through isotopic substitution. So it's a quite unstable state. Okay, so going in a more recent story of strontium titanite from the point of view of doping. So when we start to put electrons in this system that we can do through atomic substitution or to reach the lowest electronic substitution we can do through oxygen vacancies, what we can do, we can reach actually carrier concentration down to 10 to the 15 carrier per cube centimeter. But here, interestingly, we can see that now we are talking about more recent works in the last decade, and this material, for very low level of concentration, can show a quite well-defined Fermi surface. This is an experiment of Nernst effect. So how can we understand the metallicity of this system? Why we cannot see the same metallicity, for instance, for metallic silicon is due to the Bohr radius. So as it depends on the epsilon, so then we can reach the insulator metal transition ratio earlier than for other materials. Okay, so if we see at some studies about the power law dependence of the resistivity, we can see that the TQ behavior is observed, and the A coefficient is quite high. Actually, it's comparable with some heavy fermions. So this opens a question about how do we explain this behavior in such a dilute level of electronic carrier? How do we explain in the first place this increased scattering A coefficient? Okay, so another remarkable characteristic is the emergence of the superconductivity. This is the most dilute superconductor. Clearly, we can see that the critical temperature is quite low, therefore, from a technological point of view, it might be not very interesting, but it's still remarkable from a fundamental point of view. So if we look at the literature about fermiology and trying to understand which are the main underlying mechanisms, there are many open questions and unanswered questions, because mainly it's very difficult to establish what is the main mechanism and the point in which we have such a low level of electrons and which are the underlying mechanisms. So at this point, I have to say, in a historic order, I want to mention, I will not speak about heterostructure, but actually STO became again interesting because of the discovery of heterostructure. So we know that at the interface, and now it's has already almost 20 years this work, but we can see a metallic interface when we face two different insulator, perovskites. Even we can observe superconductivity. Therefore, when we look back at this point, people start to look at the precursor material, and we discovered that there are many forgotten answers, as probably you have seen in many other points, because things are less interesting or people are not putting effort, and then some questions remain open forever till, for some reason, the system becomes interesting again. So for this reason, heat transport is something that I have studied in other systems, in other contexts, and we went to study thermal transport in strontium titanite. So here I'm reporting in the study that we have carried out. It was quite it included substitution and other type of, there was a different, several questions we wanted to answer, but just to keep about what I want to talk today, that is about, that I want to talk about a special regime of transport, phonon transport. In this system, we can see, this is the curve of thermal conductivity for a pure STO sample. So we know bulk and we know substitution. We can find that there are the typical regions that we can find in textbook, so the kinetic that we believe that we understand, so that has the behavior of T to the -1, and I will go back to this point in the end of my presentation. So we have the region where phonons becomes to be more rare, and finally the ballistic region. Also this region, the ballistic region for STO would be another point of conversation because we never really reached the ballistic region. But at that point, what was interesting to us, it was this region that we call the Poiseuille flow, and why it's unusual. If we look in the literature, the typical behavior of this region, so it's T-cube mainly because of the specific heat. Okay, so we expect to have the T-cube behavior in this region. And what happened that usually between the peak that is typical of a crystal and the T-cube, we have a lower than T-cube power law. And we can see this in the large majority of material. So this is typical behavior. But there are some very little number of material that shows different behavior. For instance, bismuth, that shows an upturn. So an upturn means higher than T-cube behavior. In other words, a very efficient transport of phonons. Okay, so in STO, we observe the same. We observe in STO from different providers. So at first, we believed there was a mistake, but anyway, we confirmed that this was really true. And the question is, okay, this is what is known as hydrodynamic. I will comment more about that in the next slide. But basically, this was quite surprising to us. So why STO shows this efficient regime of transport and how we can understand. And why is relevant? Despite that, of course, here that doesn't have relevance in a technological point of view, but to understand this mechanism of efficient transport can have an important impact on different type of application because it's an efficient region of heat withdrawn. Okay, so phonon hydrodynamics is not something that we have discovered with this measurement. We have just discovered that it exists in STO. And so it's known, I mean, it was studied from in the 70s already. And what we can see is that in this old paper, of course, now we have all studies of from first principle calculations, but it's just to say that it was known for a long time. And what happened is that, I will not enter in details, but in phonon transport, we can associate some scattering time respect to different scattering mechanisms. So if we call here tau B is boundary, so phonons are limited by the physical boundary of the material. Tau N are the normal one. I will say something more about that. And tau resistive. So tau N are scattering events that preserve momentum, and tau R that degrade momentum. So a manifestation that is the experimental evidence for the hydrodynamic regime is the observation of the second sound or the Poiseuille flow. So Poiseuille flow is observed in thermal conductivity. Okay, so just to picture that in a very simple way, if we consider a 3 phonon scattering, the normal events are the ones that show a sum that fall inside the first BaBiO zone. Therefore, they conserve energy and momentum, and we don't have momentum degradation. On the contrary, when we have the sum of 2 phonons that goes out to the first BaBiO zone, then we can go back of a reciprocal lattice a vector, and therefore we have a vector that points to that direction, so we are losing, in fact, momentum. This is what we call N process and U process. Okay, we can ask when can we expect to see them? So I will make a representation against the temperature. This is very qualitatively because we have to make I have to point out something about that. But in a very general way, resistive events are the ones, why can we expect to see rather at higher temperature? So phonon branches are populated And so we have phonons that are more energetic, so it's rather more likely that they interact having a phonon, a momentum that goes out to the break-even zone. Of impurities, of course, impurities are there over the whole temperature, but yes, it's more likely the interaction when we have more phonons available for that. Anyway, of course, the impurities don't disappear with temperature. So when we go to lower temperature, phonon becomes less energetic, so we can expect to see this to happen. And finally, sorry to have the both representation, the real and the reciprocal, but ballistic is just because it represents better than we are limited by our physical geometry of the material. So this is what we need to have from a qualitative point of view, what we need to look to have hydrodynamic of phonons, so the very efficient transport regime. So are these three tau in this order? Clearly not. Otherwise, the paper that I have mentioned before, they have different hierarchy of scattering, it would not make sense. They will be fixed like that. So what happened that is between in the boundaries of these three, we can have a different hierarchy due to some characteristic of the material, okay? So, but definitely is something that we expect not at high temperature at the moment. It would be good to have this regime at high temperature. Okay, so just to summarize this very quickly, this is from the same work. So this is the textbook thermal conductivity that we expect from a material. So we have the different regimes depending on the different hierarchy of scattering time. And this region is where we expect to find it. And this is what we have observed in STO, just to place again there. So, but the question is then how can we understand the emergence of this regime in this material? So if we go back to the beginning, this material has some two prominent effects or characteristics. The one is the antiferrotic transition, and the other one is the quantum paraelectric state. These two have been observed to give rise to soft bonds in the phonon spectra. So just to remind, this is also from textbook, what we expect that can contribute to transport are phonons that are acoustic, not the optic ones. So when we are in presence of soft modes, basically are optical modes that softens, and they show a dependence with the frequency. Therefore, it's like we have additional channels to allow the scattering that preserve momentum. And this is the way that, from an observation point of view, we have interpreted our evidence. So to give a framework, there are really few solids and some very special materials that show this behavior. Recently, after our observation of STO, it was also observed in black phosphor and thin graphite. We might ask ourselves if we were not looking carefully into this view previously, not because maybe there was not. I can myself say that I have measured the thermal conductivity of graphite a few years ago, and I didn't notice that. So probably now we have a fresh look on that, and we are more carefully analyzing and looking for this special regime. So, and what makes also attractive this investigation is that there are some works. Here, I want just to mention one that was in graphene that is supposed to, it was predicted to show this regime at a bit higher temperature and not in a very limited temperature range, but there are also some other more recent work. But okay, so is a promising area that might really have impact also in the technological problem of heat withdrawn. Of course, we are interested in the basic, in the fundamentals of what we are observing, but we cannot also forget that this can have a byproduct for other areas of investigation. So now I want to turn to the high temperature part of STO that also at the time gave gave us some evidence to think about that is, so actually this is the same measurement that I have shown before, but this is just reported for the high temperature part and in terms of thermal diffusivity. So diffusivity is the physical property that governs the heat equation, is the ratio of the thermal conductivity to the specific heat. And we have observed that if we write the thermal diffusivity according to this equation, that where S is a number, is a dimensional number, then we have the square of the sound velocity, and tau p is the Planckian time. Why this equation? Actually, this was not out of the blue. This is used also in the study of bad metal. So inspired by this parallelism, we could observe that in terms of STO, we have compared STO with other insulator, and we can see that S does not fall below 1. So this raised some question at the time, that is, can we go ever below 1? Is this tau Planckian time a limit also for thermal diffusivity? And finally, we also might wonder how we are seeing the quantum grid at this temperature range, that is, that we consider that phonons are behave according to the Maxwell distribution. Therefore, how do we see that? So after this work, there was a theory work from the group of HYDRODYNAMICS, and basically their idea was to consider the melting temperature as the highest energy scale that the crystal can have. Because finally above this temperature, the crystal will melt, and therefore the crystal doesn't exist anymore, so it's the top energy scale that we can consider. So in their model, it's quite simple model. Actually, it's a harmonic oscillator with just one anharmonic term that is considered there. And they joined this with the Heisenberg uncertainty principle, consider the energy associated to the melting energy. So they defined what is called the melting velocity, and they show that the sound velocity is bound by this melting velocity. So in this model, to prove that this model makes sense, what I have done is to take a certain number of secondary data, and they have tested if the model has a sense. And what they have shown that, in fact, there is a quite close relation between the proximity to the Planckian time respect to the proximity of the sound velocity respect to the melting velocity. So this work is very interesting, but also left open some questions. Mainly the materials that have been plotted there are either cubic, so showing the highest symmetry or isotropy somehow, or they are polycrystals. Therefore, it was missing what is the role of anisotropy. So could we extend that to a different when a material shows finally anisotropy? Clearly, anisotropy in thermal conductivity and in thermal diffusivity is more rare than in other observed than in other electronic properties where it's more clearly displayed. But I just want to here mention that trying to answer this question, we have studied a material that is out of the scope of complex oxides, so I will not talk very much about that, but that is the tin selenide. Tin selenide is very famous for being a record thermoelectric material in a crystal form. So we don't need to have nanostructure on this material to have a very high figure of merit in the quantifying the efficiency as a thermoelectric material. So we have studied the thermal diffusivity in different directions, and we have seen that the theory actually works just when we take into account the anisotropic sound velocity. So therefore, we kind of pointed to, not to the limitation of the theory, but to the fact that we should look a bit farther. And going back to our interest, that is in terms of complex oxide are very wonderful functional materials, and therefore we would like to understand what happened, especially we know that going to two-dimensionality and with special engineering, we could probably have we could probably engineer also thermal transport according to the different crystal symmetry. So in this sense, I want just to give a perspective on what we are doing. Currently, we have selected another perovskite that is a BaBiO oxygen 3 that also shows emerging a collective phenomenon like superconductivity, and this material was studied quite a lot in terms of p-doping. Superconductivity has a quite complex phase diagram. It's not cubic at room temperature, it's cubic only at very high temperature, and at room temperature shows different distortion, has a tilting distortion, the breathing distortion. So definitely at room temperature, it offers a quite interesting playground to try to connect phonon behavior and in the structure. That is what we are interested. So currently we are busy with trying to measure thermal transport in two-dimensional complex oxide, actually not only BaBiO oxygen 3, but also strontium titanate itself. And so I just want to mention the people that are involved in this study. These are from my group. And here there is Valber that is busy with calculation. And it looks quite a promising playground to explore this type of physics. So in conclusion, I want to point out that thermal transport can really detect collective phonon regimes. And so the interlink between and the understanding of phonon dynamics can be quite insightful in terms of other emerging collective states. From the side of the high temperature investigation of diffusivity, is still quite an open point to understand how we could, not only how we can understand better, but how we could manipulate the structure of the material to induce special regime of transport. And finally, that BaBiO oxygen 3 is a very promising platform. I also want to quickly mention that part of the collaboration that is not our experimental expertise, but it's a joint collaboration with Valber groups. We are also busy in understanding new type of heterostructure based on BaBiO oxygen 3. So I hope very much that soon we are going to have the chance to present exciting results on that, and I want to thank you for the attention.
Thank you, Valentina, and
thank you. Very nice talk. Valentina, I have a perhaps very stupid questions to ask you, so please be kind. You showed one process of phonon scattering where you conserve momentum, and then there is this lifetime associated with it. I would expect that when you conserve momentum, you have infinite conductivity. Why do you have finite conductivity if you conserve momentum?
Because they are the dominant effect. But finally, it's in terms of thermal conductivity, you will never ever have such a perfect structure that you will, for instance, impurity finally, you always will have there.
Okay.
The other limit will be, for instance, if you go to a very thin, because at that point you invert the relation of the tau. So basically, you don't have time for normal events, and you will have the boundary events.
Okay.
So,
and one next question is the Poiseuille flow. So what is the lifetime that dominates when you, I know you had it there, but it's a lot of information. What is the lifetime that dominates when you have Poiseuille?
The tau n, the normal,
tau n.
yes, yes. Because you need that they happen more often, both of the resistive and both of the boundary.
Okay.
So they have to be the dominant, but clearly you will never get rid of the others. Especially also we have to say that we don't consider higher anharmonic terms. That finally they also can happen. So this is in a very simple, like 3 phonons. So, but there are also some more recent works that consider higher order scattering events that in reality happen. So,
sure.
Yeah.
Okay, thank you.
So, hi, Valentina. Thanks for this very nice talk. So I actually have 2 curiosities. Are you planning to do measures in a field? Because, I mean, there is all this talk about, like, topological phonons and all this stuff. I mean, and what would be the ingredients you need to get a non-trivial thermal Hall effect in these oxides? I mean, people claim this can happen in the cuprates, but I mean, do you have a feeling what would be the, let's say, the key ingredients to have these, and are you planning to measure this in a field?
So I would rather think if we would be able to observe with thermal conductivity. So my first guess would be that to see such a tiny effect, probably thermal conductivity wouldn't be the best property to use. But I also want to, I wanted to say something else. Okay, yes. Actually, we are not planning to at the moment, to measure in magnetic field. Rather, we are thinking to measure in electric field. So of course, it's not easy to push this, because, of course, it would be beautiful to be able to move this octahedra at our will. But and it's true that we can see there are already some work on that, very old work, that they apply electric field, and you can see some change in the transport. So it would be interesting to see how hydrodynamic is affected by the effect of electric field. What we are rather thinking to do is to apply electric field to a thin film. Probably we have more chance to see some effect. But this is what we are planning. Actually, this is in the plan.
Okay, thanks. And how does this Planck time appears here? I got lost. I mean, which kind of scale does it refer to in your problem? The Planck time. I mean, the Planck time you have, the Planck time you have in your.
Yes.
I mean, which scale does it refer to in your problem? What scale does it limit?
Yes. It finally defines the shortest time in which that you can have between one scattering and the other. So this is the shortest time. So there are some work also about sub-Planckian, but there are not evidence so far. So yeah, this is what it's expected at the current state of the theory also, right? So.
Thank you, Professor. About the quantum paraticity of STO, since it is used as a common substrate, is it possible that this property is propagated to the deposit film? I mean, I have a bulk that is ferroelectric and a deposit at low temperatures. It would suppress this spontaneous ferroelectricity?
So your question is whether the induced polarization can eventually make anything to any other layer that you put on top?
Yeah, if the quantum paraticity of STO at low temperatures influences the film.
Yes, I think that might be, I would expect likely that this can happen. How to quantify now, I'm not able to answer.
But, I mean, energetically they could compete, but it's possible or not, maybe.
I would expect that might be well possible. Now, if you want to tell me how can this affect a certain material that you put there? Yeah, I think it depends very much on what you're interfacing there. And finally, also what you form in the interface. Because this might finally be your leading force. Because if the interface, you finally have a different emerging state that is very prominent. So I think you need to see what you put there.
Determination would be important in this case, right? I mean, thank you.
Yeah, I'd like to ask, what is the rationale for that plot that you show with a ratio of times to a ratio of velocity for the melting and the sound?
This plot?
Yeah, why one should expect like a linearity between these things?
No, so what they have done, here I have not put all the development of the formulas. So what they have done, it's very simple. They, in their paper, the idea they use the uncertainty principle, and they have related the energy of the what they say, okay, is the highest energy that we can question this assumption, of course, but they consider higher than melting energy, there is nothing, the crystal doesn't exist. So they have put this inequality, that is actually, they end up with that, and they relate that with the scattering time that they find finally from the analysis of the oscillator. So this is really, it's very short. So what they find is, if they develop the formulas, they find that this should hold, according to their simple model.
So there the TP is the Planckian time, and tau is what?
Tau is S times tau Planck. How many times is the scattering time between one event and the other? So we could also see that. Okay, yes, it's true. I have not commented further on that. What I put in this other formula here. So S times tau P is tau. So how many times the scattering, the Planckian time is contained in my scattering event? So finally, it's the S. So if we want to see in the other way, this is the S that I'm using in the previous slide. So, and this is why we cannot go below than 1. So the idea, so we cannot go from the theory, and apparently the secondary data shows that there is quite a good agreement. We could question, there is a group of material that are completely out of this plot, but it put very small in the upper corner, so definitely it's not a closed topic, and also it's a very simple model. I mean, it's surprisingly simple. So I do believe that there is much work to do on that to understand better. And this also, it feels very qualitatively, finally. So it's just a quantum oscillator, and then they combine this energy that they say, no, this is the highest energy. So it's nice and looks like it kind of works.
But it doesn't involve the dissipation through electronic process. It's only photons.
This is just for insulators. Yes. This is just for insulator. That applies to for insulator or material that are prominently insulating, so that the resistivity finally can be high enough to be discarded. Yes.
Mm-hmm. Any other questions? Well, if not, let's thank the speakers again of this morning. Any announcement from the organizers, or? We're back here at 2.